Right now, somewhere in the depths of space, something is happening that defies everything we think we know about the universe. In less time than it takes you to blink, actually, in a thousandth of that time, an explosion of radio waves is erupting with more energy than our sun will produce in 3 days. We thought cosmic events needed time to build power, that the brightest phenomena in the universe required massive scale and duration. We were completely wrong. These are fast radio bursts, and they represent one of the most disturbing mysteries in modern astronomy. Picture this. In the time it takes a hummingbird to flap its wings once, these cosmic phenomena release more energy than 500 million suns. They last mere milliseconds. Blink and you miss an entire galactic-scale explosion. Yet, in that impossibly brief moment, they can outshine entire galaxies containing billions of stars, each burning for billions of years. Here's what makes this truly unsettling. We've only known about fast radio bursts since 2007, which means they've been occurring throughout cosmic history while we remained completely oblivious. Every day, thousands of these millisecond monsters are erupting across the observable universe, each one a cosmic scream of energy that arrives at Earth as nothing more than a faint radio whisper. The first one we detected was so powerful and so brief that astronomers initially thought their equipment had malfunctioned. Dr. Duncan Lorimer of West Virginia University discovered that first burst in archived data, a signal so unexpected that it took years for the scientific community to accept its reality. The Lorimer burst, as it came to be known, lasted just 5 milliseconds, but carried the energy signature of something that should have taken thousands of years to accumulate. When astronomers traced its origin, they found it came from a region of space containing nothing but darkness. No visible galaxy, no obvious source, just empty cosmic void somehow producing the energy output of a small star's entire lifetime in less time than it takes to snap your fingers. Tonight, we're going to uncover what fast radio bursts reveal about the hidden violence of our universe. You'll discover how these millisecond flashes challenge our fundamental understanding of time, energy, and cosmic scale. We'll explore the technological detective story of how scientists hunt for signals that disappear before most instruments can even register them, and we'll examine the terrifying possibility that our galaxy might be constantly bathed in energies powerful enough to sterilize planets, energies we only now beginning to detect. The story of fast radio bursts is fundamentally a story about the limits of human perception and the shocking realities that exist beyond our everyday experience. These phenomena force us to confront an uncomfortable truth. The universe operates on timescales and energy scales that make even our most extreme earthly experiences seem quaint by comparison. When you understand what's happening during a fast radio burst, you begin to realize that our planet exists in a cosmic environment far more dynamic and dangerous than we ever imagined. Consider this. Astronomers estimate that fast radio bursts occur roughly once every 10 seconds somewhere in the observable universe. This means that in the time you've been reading these words, dozens of cosmic explosions have erupted with the power to outshine entire galactic neighborhoods. Each one represents a cosmic event so extreme that a single burst could power human civilization for longer than our species has existed. Yet they flash and vanish in timescales so brief that even light, the fastest thing in the universe, can barely traverse the distance of Earth's diameter during their entire duration. What we've learned about fast radio bursts challenges our most basic assumptions about how the universe works. We assumed that powerful meant long-lasting, that brief meant weak, that distant meant faint. Fast radio bursts violate all these assumptions simultaneously. They reproving that the universe contains mechanisms for concentrating and releasing energy that we only beginning to understand. Mechanisms that operate on principles we haven't yet discovered. The hunt for these cosmic ghosts has led astronomers to develop the most sensitive radio telescopes in human history. instruments capable of detecting whispers from galaxies billions of light-years away. The Canadian Hydrogen Intensity Mapping Experiment CHIME can scan the entire northern sky every day, waiting for the radio signature of these millisecond monsters. In just its first year of operation, CHIME detected more fast radio bursts than all previous telescopes combined, revealing that our universe is absolutely saturated with these brief cosmic screams. But here's where the mystery deepens. Despite detecting hundreds of these bursts, we still don't know what causes them. The leading theories involve some of the most extreme objects in the universe. Magnetars with magnetic fields trillions of times stronger than Earth's neutron stars spinning hundreds of times per second, or even more exotic. Phenomena that push the boundaries of known physics. Each theory attempts to explain how nature can concentrate the energy of millions of suns into a package small enough to release in milliseconds. If you're fascinated by cosmic mysteries that challenge everything we think we know about space and time, subscribe and hit the thumbs up. And here's something to consider. If fast radio bursts have been occurring throughout cosmic history, could ancient bursts have influenced the development of life on Earth? Comment below with your thoughts. I'll pin the most intriguing theory. What makes fast radio bursts particularly fascinating is that they represent a completely new category of cosmic phenomenon. Unlike supernovas, which build up over millions of years before exploding, or black hole mergers, which spiral inward for eons before their final collision, fast radio bursts appear to come from nowhere and vanish just as quickly. They're like cosmic lightning, brief, powerful, and fundamentally different from the slow-burning processes we thought dominated the universe. The implications are staggering. If objects exist that can concentrate galactic-scale energies into millisecond bursts, what does this tell us about the hidden architecture of reality? What fundamental principles of physics are we missing that would allow such extreme concentration and release of energy? These questions aren't just academic curiosities. They are pointing toward gaps in our understanding of the universe that could revolutionize physics itself. Now let's begin our journey into the millisecond universe, where time itself becomes a prison and energy operates by rules we're only starting to comprehend. Chapter 1. Cosmic Flash. The story of fast radio bursts begins with a cosmic accident, or rather, with an astronomer's curiosity about cosmic accidents that had already happened. In 2007, Duncan Lorimer was doing what astronomers often do, digging through old data, looking for patterns that might have been missed the first time around. He was examining pulsar observations from the Parkes Observatory in Australia, routine measurements of spinning neutron stars that had been archived years earlier. What he found would completely revolutionize our understanding of the radio universe. Hidden in data from July 24, 2001, Lorimer discovered something that shouldn't have existed according to everything astronomers thought they knew about cosmic radio sources. The signal lasted exactly 5.06 milliseconds, appeared to come from far beyond our galaxy, and carried more energy than seemed physically possible for such a brief event. The signal was so unexpected, so contrary to established astronomical wisdom, that Lorimer initially suspected equipment malfunction or terrestrial interference. But the signal had characteristics that marked it as genuinely cosmic. Its radio frequency components arrived at slightly different times, with higher frequencies arriving fractionally before lower ones, a phenomenon called dispersion that only occurs when radio waves travel through the ionized gas of intergalactic space. The amount of dispersion indicated the signal had traveled through space for billions of years, meaning its source lay in the deep universe, far beyond the boundaries of the Milky Way. This created an immediate paradox. For a radio signal to be detectable across such vast distances, its source would need to be extraordinarily powerful. But for it to last only 5 milliseconds suggested something equally extraordinary about the mechanism producing it. Traditional cosmic radio sources, Pulsars, quasars, radio galaxies operated on much longer timescales. Pulsars might pulse hundreds of times per second, but each pulse was part of a continuous, predictable pattern. This signal was different. It appeared once and never repeated. When Lorimer calculated the energy requirements for his mystery signal, the numbers were disturbing. In those 5 milliseconds, the source had released more energy in radio waves alone than the sun produces across all wavelengths in an entire day. This wasn't just unusual. It violated basic assumptions about how cosmic objects behave. Nothing in the known universe could concentrate that much energy into such a brief burst while remaining completely invisible at all other times. The scientific community's initial reaction was skepticism. Single, unrepeated events are notoriously difficult to verify in astronomy, where reproducibility is often impossible and equipment glitches are common. For years, the Lorimer burst remained a curious anomaly, filed away as an interesting mystery, but not something that demanded immediate attention from the broader astronomical community. Everything changed in 2013 when Dan Thornton and his colleagues published evidence for 4 more similar bursts, each detected independently by different telescopes. The bursts showed the same characteristics as Lorimer's original discovery: brief duration, high energy, and dispersion signatures indicating extragalactic origin. Suddenly, astronomers realized they weren't dealing with a single mysterious event, but rather with an entirely new class of cosmic phenomenon. The term fast radio burst was coined to describe these millisecond monsters, and the hunt was on. Radio astronomers around the world began developing new techniques for detecting brief, powerful signals buried in the constant background noise of the radio universe. The challenge was immense. Imagine trying to spot a camera flash in broad daylight while wearing sunglasses and looking through a dirty window. Fast radio bursts are cosmic whispers by the time they reach Earth, yet they represent some of the most energetic events in the universe. What makes these signals particularly elusive is their unpredictability. Unlike pulsars, which pulse with clockwork precision, or variable stars, which brighten and dim on predictable cycles, fast radio bursts seem to occur randomly in both space and time. This randomness makes them incredibly difficult to study systematically. You can point a telescope at a specific location and wait for a fast radio burst to occur. You have to monitor vast areas of sky continuously, hoping to catch one in the act. The breakthrough came with the development of new detection algorithms and more sophisticated radio telescopes. The Australian Square, Kilometre Array Pathfinder, ASCAT, and the Canadian Hydrogen Intensity Mapping Experiment, CHIME, revolutionized fast radio burst astronomy by providing both the sensitivity to detect faint signals and the field of view to monitor large portions of the sky simultaneously. CHIME, in particular, represents a masterpiece of modern radio astronomy. Rather than using a traditional dish that can only point in one direction at a time, CHIME consists of 4 enormous half-pipe antennas that can electronically scan the entire overhead sky as Earth rotates. Every day, CHIME sees roughly half the entire universe pass overhead, making it an incredibly efficient fast radio burst hunting machine. Within months of beginning operations, CHIME had detected more fast radio bursts than all previous telescopes combined. The flood of new discoveries revealed that these events are far more common than anyone had suspected. Current estimates suggest that fast radio bursts occur roughly once every 10 seconds somewhere in the observable universe, meaning thousands happen every day across the cosmic landscape. But frequency isn't the only revelation emerging from modern fast radio burst surveys. Each new detection provides clues about the extreme physics operating during these millisecond events. Some bursts show evidence of rotation, suggesting their sources are spinning rapidly. Others display polarization patterns that indicate incredibly strong magnetic fields. A few have been detected across multiple radio frequencies simultaneously, allowing astronomers to study how the burst energy is distributed across the electromagnetic spectrum. Perhaps most intriguingly, some fast radio bursts have now been observed to repeat, producing multiple bursts from the same cosmic location over periods of months or years. These repeating sources provide unprecedented opportunities to study the mechanisms behind fast radio burst production, since astronomers can predict roughly where and when future bursts might occur. The repeating fast radio, first known as FRB 121102, has become the most intensively studied object in this new field. Located in a small galaxy about 3 billion light-years away, this source has produced hundreds of individual bursts since its discovery. Each burst lasts only milliseconds, but together they're providing a detailed picture of the extreme environment surrounding the burst source. What we've learned from studying these cosmic flashes challenges fundamental assumptions about energy, time, and cosmic violence. Fast radio bursts represent a completely new category of astronomical phenomenon, events that operate on timescales far shorter than traditional astronomical processes, yet release energies comparable to some of the most powerful events in the universe. The mystery of what produces these millisecond monsters will lead us next into the hidden mechanisms of cosmic energy concentration, where we'll discover that the universe has ways of storing and releasing power that push the very boundaries of known physics. Chapter 2: Hidden Power. To understand the true magnitude of what happens during a fast radio burst, we need to confront numbers that strain human comprehension. When astronomers first calculated the energy output of these millisecond events, they discovered something that seemed to violate the basic laws of cosmic physics. Mechanisms capable of concentrating and releasing more power than entire stars produce over decades, all compressed into time frames shorter than a single heartbeat. Consider the energy scale we're dealing with. A typical fast radio burst releases approximately 1034 joules of energy in radio waves alone. That is roughly equivalent to the total energy output of our sun over 3 full days, concentrated into a flash lasting less than 5 milliseconds. To put this in perspective, if you could somehow capture and store the energy from a single fast radio burst, it would power the entire United States for longer than human civilization has existed. But raw energy numbers only tell part of the story. What makes fast radio bursts truly extraordinary is their power output, energy per unit time. During the brief moments when these cosmic events are active, they can generate power levels exceeding watts. This is more power than flows through the combined electricity grids of every nation on Earth, multiplied by a trillion. For those few milliseconds, a fast radio burst source becomes one of the most luminous objects in the radio universe. The concentration of this energy into such brief timescales implies physical processes that operate far beyond anything we observe in everyday cosmic phenomena. Most astronomical events that produce comparable energies, supernova, gamma ray bursts, quasar outbursts, build up their energy over much longer periods. A supernova might take millions of years to develop before exploding over several weeks. A gamma ray burst typically lasts seconds to minutes. Fast radio bursts compress similar energy scales into thousandths of a second. This compression creates what physicists call an energy density problem. For such enormous energies to be released so quickly, they must be stored in incredibly compact volumes with extraordinary efficiency. The source region of a fast radio burst can be no larger than the distance light travels in milliseconds, roughly 300 kilometers. This means we're looking at astronomical objects capable of storing and releasing stellar-scale energies from regions smaller than most large asteroids. Dr. Avi Loeb of Harvard University has calculated that the brightness temperature of fast radio burst sources, a measure of how concentrated their energy is, can exceed 1037 Kelvin. This is trillions of times hotter than the core of the Sun and approaches theoretical limits for how concentrated electromagnetic energy can become before the fundamental structure of spacetime itself begins to break down. The leading theoretical candidates for fast radio burst sources all involve some of the most extreme objects known to exist in the universe. Neutron stars, the collapsed cores of massive stars, represent one promising possibility. These objects pack more mass than the Sun into volumes smaller than Manhattan, creating gravitational fields so intense that a sugar cube of neutron star material would weigh as much as Mount Everest on Earth. But even neutron stars, as extreme as they are, struggle to explain fast radio burst energetics without invoking additional exotic physics. The most promising models involve magnetars neutron stars with magnetic fields roughly 1 trillion times stronger than Earth's magnetic field. These cosmic magnets are so powerful that they would erase the magnetic strip on a credit card from half the distance to the moon. And their magnetic fields are strong enough to distort the quantum vacuum of space itself. When a magnetar undergoes what astronomers call a starquake, a sudden rearrangement of its ultra-dense crustal material, it can release magnetic energy equivalent to what the Sun produces over centuries. The rapid reconfiguration of magnetic field lines around such an object could theoretically generate the intense, brief radio bursts we observe. The magnetic field energy gets converted to electromagnetic radiation through processes involving particle acceleration to nearly the speed of light. Recent observations have provided tantalizing evidence supporting the magnetar hypothesis. In April 2020, astronomers detected a fast radio burst-like signal from SGR 1935-2154, a known magnetar within our own galaxy. This was the first time a fast radio burst had been associated with a specific, identified astronomical object, and it provided crucial insights into the physics of burst production. The galactic fast radio burst was roughly 1 million times weaker than typical extragalactic bursts, but its relative proximity allowed astronomers to study it in unprecedented detail. The burst coincided with a high-energy X-ray flare from the magnetar, suggesting a direct connection between magnetic field reconfiguration and radio burst production. This observation finally provided a smoking gun linking fast radio bursts to magnetar activity. However, the magnetar explanation faces significant challenges when applied to the most energetic fast radio bursts. Some extragalactic bursts release energies that would require multiple magnetars acting simultaneously, or individual magnetars undergoing events far more extreme than anything observed in our galaxy. This has led astronomers to consider even more exotic possibilities. One intriguing alternative involves interactions between neutron stars and their environments. If a magnetar exists within the dense stellar wind of a massive companion star, or if it's actively accreting material from a companion, the complex magnetic interactions could potentially amplify burst energies beyond what isolated magnetars can produce. These environmental models attempt to explain the most energetic, fast radio bursts by invoking complex multi-object systems. Even more speculative theories venture into truly exotic territory. Some models propose that fast radio bursts could result from the collapse of strange quark matter, hypothetical ultra-dense material composed of fundamental particles called quarks, rather than the protons and neutrons found in normal matter. Others suggest they might be signatures of cosmic string interactions, one-dimensional defects in spacetime left over from the early universe. Perhaps most remarkably, some fast radio bursts appear to release their energy in highly structured patterns. Rather than random radio noise, these events produce organized, coherent radiation that suggests the underlying physical process operates with extraordinary precision. This coherence implies that whatever mechanism produces fast radio bursts can maintain quantum mechanical organization across astronomical distances and timescales. The coherent nature of fast radio burst radiation creates additional puzzles for theoretical models. Maintaining coherence in high-energy astrophysical processes typically requires very specific conditions, synchronized particle motions, carefully aligned magnetic fields, or other forms of cosmic cooperation that are difficult to achieve and maintain in chaotic astronomical environments. Recent discoveries have revealed that some fast radio bursts exhibit internal structure on microsecond timescales, variations in intensity that occur faster than the overall burst duration. These subbursts suggest that the underlying emission mechanism operates with even finer temporal control than previously suspected, adding additional layers of complexity to an already challenging theoretical puzzle. The study of fast radio burst energetics has also revealed surprising connections to other astronomical phenomena. Some bursts appear to be associated with gamma ray emissions, suggesting that the same physical processes that produce intense radio waves might also generate high-energy photons. This multi-wavelength connection provides additional observational constraints that theoretical models must satisfy. What emerges from studying fast radio burst energetics is a picture of cosmic processes operating at the absolute limits of what physics allows. These events represent the universe's most efficient mechanisms for converting stored energy into electromagnetic radiation, achieving power densities that approach fundamental physical limits. Understanding how such extreme energy concentration and release occurs requires us to explore the boundaries where conventional physics begins to break down and exotic new phenomena might emerge. The hidden power of fast radio bursts forces us to confront the possibility that our universe contains energy storage and release mechanisms far beyond anything we've previously imagined. Mechanisms that could revolutionize our understanding of how cosmic objects can manipulate energy, time, and space itself. Chapter 3. Impossible Scale. When astronomers first began mapping the distribution of fast radio bursts across the cosmos, they discovered something that fundamentally challenged our understanding of cosmic scale and distance. These millisecond events weren't just occurring in our local galactic neighborhood. They were erupting from the most distant reaches of the observable universe, some from galaxies so far away that their light has been traveling toward us for over half the age of the universe itself. The scale implications are staggering. Fast radio bursts have been detected from distances exceeding 8 billion light-years, meaning we're observing cosmic violence that occurred when the universe was less than half its current age. At such distances, entire galaxy clusters appear as mere points of light, yet somehow these brief radio flashes can still be detected by our terrestrial instruments. This represents an almost incomprehensible achievement in both cosmic energy generation and human technological capability. To appreciate the true scale of what we're dealing with, consider that a fast radio burst detected from 3 billion light-years away has traveled through space for longer than complex life has existed on Earth. During that journey, the radio waves have passed through vast expanses of intergalactic medium, survived encounters with dark matter concentrations, and navigated the gravitational fields of countless intervening galaxies, all while maintaining enough coherent energy to trigger our detectors when they finally arrive. The distance scale of fast radio bursts provides astronomers with a powerful new tool for probing the large-scale structure of the universe. As radio waves travel through intergalactic space, they interact with the diffuse plasma that fills the voids between galaxies. This interaction causes dispersion, the same effect that creates rainbows when sunlight passes through water droplets, but on a cosmic scale that encodes information about everything the radio waves encountered during their billion-year journeys. Dr. Jean-Pierre Macquart and his colleagues have shown how fast radio burst dispersion measurements can be used to weigh the universe, providing independent estimates of how much normal matter exists in the cosmic web of filaments and voids that connects all galaxies. This technique, known as the Macquart relation, transforms each fast radio burst into a cosmic probe capable of sensing matter distributions across billions of light-years. The scale revelations don't stop with distance. When astronomers trace fast radio bursts back to their host galaxies, they find these events occurring in cosmic environments spanning an enormous range of galactic types, ages, and compositions. Some bursts originate from massive, actively star-forming galaxies containing hundreds of billions of stars. Others come from small, quiescent dwarf galaxies with stellar populations older than our solar system. This diversity suggests that whatever produces fast radio bursts represents a fundamental cosmic process that can operate across the full spectrum of galactic environments. Unlike some astronomical phenomena that require specific conditions, such as gamma-ray bursts, which typically occur in actively star-forming regions, fast radio bursts appear to be truly universal cosmic events. Perhaps most remarkably, the host galaxy studies have revealed that fast radio bursts can occur in cosmic environments we previously thought were too evolved or too quiet to produce such energetic events. Some of the most distant fast radio bursts originate from what astronomers call red and dead galaxies, ancient stellar systems that exhausted their star formation fuel billions of years ago and should, theoretically, lack the young massive stars needed to create exotic compact objects. This observation forces astronomers to consider that fast radio burst sources might have much longer lifetimes than initially suspected, or that they can be produced by stellar evolutionary pathways that don't require recent star formation. Some models now propose that certain types of neutron stars or magnetars could remain capable of producing fast radio bursts for billions of years after their initial formation, essentially becoming cosmic time bombs that can explode into radio visibility long after their parent galaxies have settled into quiescence. The scale of fast radio burst detection has also revealed surprising patterns in how these events are distributed across cosmic time. By studying bursts at different distances, and therefore different look-back times, astronomers can reconstruct how fast radio burst production rates have changed throughout cosmic history. Initial results suggest that these events were even more common in the early universe than they are today, possibly reflecting differences in star formation rates, galaxy interactions, or fundamental cosmic conditions. One of the most mind-bending aspects of fast radio burst scale involves the concept of cosmic simultaneity. When we detect a fast radio burst from a galaxy 5 billion light-years away, we're seeing an event that actually occurred 5 billion years ago, when our own solar system was just forming from a disk of cosmic debris. This means that the exotic astronomical object producing that burst might have evolved, changed, or even ceased to exist entirely during the light travel time to Earth. The scale implications extend beyond simple distance to encompass the fundamental question of cosmic evolution. Fast radio bursts provide snapshots of extreme physics operating throughout cosmic history, allowing astronomers to study how the universe's most energetic processes have changed as cosmic conditions evolved. The early universe was denser, hotter, and more chaotic than today, conditions that might have made certain types of fast radio burst sources more common or more energetic. Recent observations have begun to reveal correlations between fast radio burst properties and cosmic distance, suggesting that the physical processes producing these events might indeed have evolved over cosmic time. Some distant bursts show different spectral characteristics or duration distributions compared to nearby events, hinting at fundamental changes in burst production mechanisms as the universe aged and cooled. The scale of fast radio burst science has also pushed technological capabilities to extraordinary limits. Detecting a millisecond radio signal from billions of light-years away requires instruments sensitive enough to measure energy levels comparable to the light from a single candle observed from the distance of the Moon. This achievement represents one of the most sophisticated examples of cosmic signal detection ever accomplished by human technology. Modern fast radio burst surveys monitor volumes of space containing millions of galaxies simultaneously, waiting for the brief radio flash that signals another cosmic explosion. The Australian Square Kilometre Array, Pathfinder, can survey roughly 30 square degrees of sky, an area 60 times larger than the full moon, with sufficient sensitivity to detect fast radio bursts out to cosmological distances. This represents a monitoring capability that would have been considered impossible just decades ago. The scale challenges don't end with detection. Each fast radio burst carries information encoded in its radio signal that can reveal details about cosmic environments across vast distances. The polarization of fast radio burst radiation, for example, can be rotated by magnetic fields anywhere along the signal's billion light-year journey, providing a cumulative measurement of magnetic field strength throughout intergalactic space. These magnetic field measurements are revealing that the cosmic web, the network of filaments and voids that defines large-scale cosmic structure, is pervaded by magnetic fields with strengths and geometries that were previously unknown. Fast radio bursts are essentially acting as cosmic flashlights, illuminating magnetic field structures across scales ranging from individual galaxies to the largest cosmic structures. The impossible scales revealed by fast radio burst. Astronomy forces to confront the remarkable fact that cosmic violence can be detected and studied across distances that challenge human comprehension. These millisecond events connect us directly to physical processes occurring at the edge of the observable universe, providing real-time glimpses of cosmic evolution spanning half the age of time itself. Understanding these scale relationships requires us to develop new conceptual frameworks for thinking about cosmic causation, temporal relationships, and the fundamental interconnectedness of astronomical phenomena across the largest possible scales of space and time. Chapter 4. Ancient signals. Every fast radio burst we detect carries within its radio waves an encoded history of the universe itself. These cosmic time capsules have traveled through space for billions of years, accumulating signatures from every significant structure they encountered during their epic journeys from the distant cosmos to Earth. When astronomers decode these signals, they rereading messages written in the language of physics across scales of space and time that dwarf human experience. The journey of a fast radio burst begins in the exotic environment surrounding its source, likely a magnetar or other ultra-compact object where magnetic fields are strong enough to tear apart atomic nuclei and space-time itself approaches its limits of stability. From this violent birthplace, the radio waves expand outward at the speed of light, carrying the electromagnetic imprint of whatever catastrophic process created them. Within the first few light years of their journey, these radio waves encounter the complex environment of their host galaxy. They pass through stellar winds from massive stars, navigate around supernova remnants still expanding from ancient stellar explosions, and thread their way through the galaxy's magnetic field, a sprawling, invisible architecture that can extend for hundreds of thousands of light years. Each interaction leaves its mark on the radio signal, slightly altering the wave properties in ways that encode information about galactic conditions. Dr. Vikram Ravi of Caltech has pioneered techniques for extracting this environmental information from fast radio burst signals, essentially using them as probes of galactic physics across cosmic time. The polarization rotation of the radio waves reveals magnetic field strengths and orientations, while subtle frequency-dependent delays indicate the density and distribution of ionized gas throughout the host galaxy. As fast radio bursts escape their host galaxies and enter the vast emptiness of intergalactic space, they begin an even more remarkable phase of their journey. The space between galaxies isn't truly empty. It's filled with an incredibly tenuous plasma consisting of roughly 1 proton per cubic meter, along with dark matter structures, invisible to direct observation, but detectable through their gravitational effects on passing radiation. This intergalactic medium represents one of the universe's most important yet least understood components. It contains roughly half of all the normal matter that exists, yet it is so diffuse that its presence was only confirmed in recent decades through sophisticated X-ray observations and theoretical modeling. Fast radio bursts provide the first direct way to probe this cosmic web of matter across the vast distances where it shapes the large-scale structure of the universe. The dispersion of fast radio burst signals, the slight delay of lower radio frequencies compared to higher ones, directly measures the total amount of ionized matter along the entire line of sight from source to Earth. This includes contributions from the host galaxy, intervening galaxies, and the diffuse intergalactic medium. By carefully accounting for known galactic contributions, astronomers can isolate the intergalactic component and use it to map matter distributions across cosmic scales. Perhaps most remarkably, some fast radio bursts show evidence of having passed through the halos of intervening galaxies during their journey to Earth. These cosmic encounters create additional dispersion signatures that can reveal the presence of otherwise invisible galactic structures. Dr. Clancy James of Curtin University has used these galactic intersection events to study how matter is distributed in the outer regions of galaxies, far beyond where optical telescopes can detect stellar light. The ancient nature of fast radio burst signals becomes most apparent when astronomers consider the cosmic evolution they've witnessed during their travels. A burst detected from 6 billion light-years away began its journey when the universe was only about half its current age, when star formation rates were much higher, when galaxies were more actively merging and interacting, and when the overall cosmic environment was dramatically different from today's relatively mature, organized universe. These radio time travelers carry information about cosmic conditions that existed billions of years before Earth even formed. They encode data about galaxy formation processes, early stellar populations, and the evolution of cosmic magnetic fields during epochs we can study in no other way. Each fast radio burst essentially provides a core sample through cosmic history, revealing layers of information about how the universe developed over vast timescales. The time delay between radio frequencies in fast radio burst signals also provides one of the most precise measurements available for studying cosmic expansion. As the universe expands, it stretches the wavelengths of all electromagnetic radiation traveling through it, an effect known as cosmological redshift. The accumulated dispersion along a fast radio burst S-path encodes information about how cosmic expansion rates have changed over the burst's travel time. Dr. Lachlan Marnock and colleagues have shown that large samples of fast radio bursts could potentially provide independent measurements of cosmic expansion history, complementing and cross-checking results from supernova observations and other cosmological probes. This application transforms each burst into a cosmic ruler capable of measuring distances across billions of light-years with unprecedented precision. Some of the most ancient fast radio bursts detected to date originated when the universe was undergoing fundamental changes in its large-scale properties. During the epoch when these signals began their journey, the cosmic web was still forming dark matter halos were actively assembling, and the intergalactic medium was being enriched with heavy elements from the first generations of stars to form and explode. The radio waves from these ancient events have thus witnessed cosmic evolution spanning half the age of the universe. They carry embedded information about how magnetic fields developed throughout cosmic structure, how matter became distributed across increasingly large scales, and how the universe transitioned from its early, chaotic state to the relatively organized cosmos we observe today. Recent studies have begun to reveal systematic differences between the properties of ancient fast radio bursts and those originating from the local universe. Some distant bursts show broader spectral characteristics, suggesting that the emission mechanisms might have operated differently in the early universe's more extreme environment. Others display polarization signatures that hint at stronger or more organized magnetic fields in young galaxies compared to their modern counterparts. These evolutionary signatures are opening new windows into cosmic history that complement traditional astronomical approaches. While optical telescopes can observe ancient galaxies directly, they primarily detect light from the brightest, most massive stellar systems. Fast radio bursts potentially sample a much broader range of cosmic environments, including small, faint galaxies that would be impossible to study through conventional means. The encoding of cosmic history in fast radio burst signals extends beyond simple environmental measurements to include information about fundamental physics operating under extreme conditions. The coherence and polarization properties of these signals probe how electromagnetic radiation behaves in magnetic field environments that are trillions of times stronger than anything achievable in terrestrial laboratories. Some theoretical models suggest that fast radio burst propagation through cosmic magnetic fields could reveal signatures of exotic physics, including possible violations of fundamental symmetries or evidence for magnetic monopoles, hypothetical particles that have never been conclusively detected but are predicted by some theories of quantum gravity. The ancient signals encoded in fast radio bursts are teaching us that the universe operates as an integrated information processing system where cosmic events create electromagnetic messages that travel across space and time, carrying data about the conditions and processes that shaped cosmic evolution. These millisecond messengers connect us directly to the deepest history of space and time, providing real-time access to information about cosmic epochs that would otherwise remain forever beyond human observation. Each fast radio burst thus represents both an individual cosmic catastrophe and a billion-year journey through the evolving universe, making these brief events some of the most information-rich phenomena in all of astronomy. Chapter 5. Detection War: The Hunt for Fast Radio. Bursts represents one of the most technically challenging endeavors in modern astronomy, requiring instruments sensitive enough to detect signals billions of times fainter than a cell phone transmission while maintaining the temporal resolution to capture events that last mere milliseconds. This cosmic detective story has driven innovations in radio telescope design, signal processing, and data analysis that push the boundaries of what human technology can achieve. The fundamental challenge facing fast radio burst hunters stems from the extreme mismatch between the cosmic scale of these events and their fleeting nature. While the sources generate radio powers that can outshine entire galaxies, the signals arrive at Earth as whispers barely distinguishable from the constant background noise of cosmic radiation. Detecting them requires radio telescopes capable of monitoring vast areas of sky with extraordinary sensitivity, while processing data streams that can exceed terabytes per hour. Before the development of modern fast radio burst surveys, radio astronomy was dominated by targeted observations of known sources, pulsars, quasars, and radio galaxies whose positions were well established and whose signals could be studied through long integrations. Fast radio bursts shattered this paradigm by demanding wide-field, real-time monitoring capabilities that didn't exist when the first bursts were discovered. The breakthrough came with the development of interferometric arrays, collections of smaller radio dishes that work together to create the equivalent of much larger telescopes while maintaining the ability to observe multiple directions simultaneously. The Australian Square Kilometre Array Pathfinder, ASCAP, pioneered this approach with 36 identical 12-meter dishes spread across several kilometers of the Murchison Radio Astronomy Observatory in Western Australia. ASKAP's revolutionary capability lies in its phased array feed systems, electronic devices that can simultaneously create multiple telescope beams from each dish, effectively multiplying the telescope's observing power by factors of dozens. With this technology, ASKAP can monitor roughly 1,000 square degrees of sky simultaneously, an area equivalent to 4,000 full moons, while maintaining the sensitivity needed to detect fast radio bursts from cosmological distances. But even ASKAP pales in comparison to the most successful fast radio burst hunting machine ever constructed, the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME. Located in the mountains of British Columbia, CHIME consists of 4 enormous half-pipe antennas, each 100 meters long and 20 meters wide, that work together to monitor the entire overhead sky as Earth rotates. Dr. Kiyoshi Masui, one of CHIME's principal investigators, describes the telescope as a cosmic search engine, capable of processing radio data streams equivalent to the entire global internet traffic. Every day, CHIME generates roughly 10 terabytes of raw data, enough to fill hundreds of thousands of photographs that must be analyzed in real time to identify fast radio burst candidates buried within the noise. The signal processing challenges are staggering. CHIME's correlator system performs 13 million billion mathematical operations per second, searching for brief coherent signals across thousands of frequency channels simultaneously. The system must identify potential fast radio bursts within seconds of their detection, triggering follow-up observations with other telescopes before the radio echo fades below detectability. This real-time processing requirement has driven innovations in machine learning and artificial intelligence applications to astronomy. Modern fast radio burst detection systems employ neural networks trained on thousands of simulated bursts to distinguish genuine cosmic signals from terrestrial interference. These AI systems can recognize fast radio burst signatures with accuracy rates exceeding 95%, dramatically reducing the false positive rates that plagued early detection attempts. The war against interference represents perhaps the greatest ongoing challenge in fast radio burst astronomy. Radio frequencies are increasingly crowded with human-generated signals. Cell phones, satellite communications, radar systems, and countless other electronic devices that produce radio emissions capable of mimicking cosmic signals. Distinguishing genuine fast radio bursts from this technological cacophony requires sophisticated filtering algorithms and multiple confirmation methods. Dr. Emily Petroff of the University of Amsterdam has pioneered techniques for characterizing and rejecting RDI of frequency interference, developing databases of known interference patterns that can be automatically identified and removed from fast radio burst search pipelines. Her work revealed that many early fast radio burst candidates were actually terrestrial signals, including some that originated from microwave ovens opening while still running. The detection war has also driven innovations in telescope sighting and design. The most sensitive fast radio burst searches now operate in radio quiet zones, remote locations where radio frequency interference is minimized through geography and regulation. The Murchison Radio Astronomy Observatory, where SKAP operates, is located in one of the most radio-quiet environments on Earth, hundreds of kilometers from major population centers and protected by Australian radio astronomy regulations. International cooperation has become essential as fast radio burst astronomy has matured. No single telescope can monitor the entire sky continuously, so astronomers have developed networks of coordinated facilities that can provide follow-up observations when initial detections occur. The Fast Radio Burst Detection Network now spans the globe, with facilities in Australia, Canada, South Africa, China, and other countries working together to characterize these brief cosmic events. One of the most sophisticated examples of this coordination involves the real-time alert systems that can trigger rapid follow-up observations. When CHIME detects a fast radio burst, automated systems can alert optical and X-ray telescopes within minutes, allowing astronomers to search for associated emission at other wavelengths. These multi-messenger observations have revealed that some fast radio bursts are accompanied by high-energy photon emission, providing crucial insights into the physics of burst production. The detection challenges have also spurred development of new analysis techniques that can extract maximum information from minimal data. Dr. Ziggy Plonis of McGill University has developed methods for analyzing fast radio burst substructure on microsecond timescales, revealing internal complexity within these brief events that provides clues about emission mechanisms and source environments. Recent advances have pushed detection capabilities to extraordinary limits. The Deep Synoptic Array, under construction in California, will eventually consist of 110 radio dishes working together to provide both high sensitivity and precise localization of fast radio bursts. This facility will be capable of pinpointing burst sources to individual galaxies within seconds of detection, enabling rapid multi-wavelength follow-up studies. The technical arms race has also extended to space-based fast radio burst detection. The proposed Farview Observatory would place fast radio burst detectors on the far side of the Moon, completely shielded from Earth's radio interference. Such a facility could achieve sensitivities impossible from Earth's surface while monitoring the entire visible universe continuously. Perhaps most remarkably, the detection war has revealed just how common fast radio bursts actually are. Early estimates suggested these events occurred perhaps once per day across the entire observable universe. Modern surveys indicate the true rate is closer to 10,000 per day, meaning that every second, multiple fast radio bursts are erupting somewhere in the cosmos, most of them too faint or poorly positioned for our current generation of telescopes to detect. This abundance suggests that fast radio bursts represent a fundamental cosmic process, not rare catastrophic events. The challenge now facing astronomers is not finding fast radio bursts, but rather understanding what the flood of new detections reveals about the violent universe surrounding us. Every technical advance in detection capability brings with it new puzzles about the nature and origin of these mysterious cosmic messengers. The detection war continues to escalate as astronomers push toward the ultimate goal: detecting fast radio bursts in real time with sufficient precision to enable immediate multi-wavelength follow-up observations. This capability would transform fast radio burst astronomy from a statistical science based on large samples to a precision science capable of studying individual burst events in unprecedented detail. Chapter 6: Energy Mystery, the fundamental puzzle at the heart of fast radio. Burst physics isn't just the enormous energies involved. It asks how such energies can be generated, stored, and released through mechanisms that violate our basic understanding of how cosmic objects should behave. When theoretical physicists attempt to model fast radio burst emission, they consistently run into barriers where conventional physics breaks down and exotic new phenomena must be invoked. The energy mystery begins with a simple question: how can any astronomical object concentrate enough power to outshine entire galaxies while operating on timescales shorter than a single lightning flash? The answer requires us to explore the absolute limits of what matter can accomplish under the most extreme conditions the universe can create. Dr. Bing Zhang of the University of Nevada, Las Vegas, has calculated that fast radio burst sources must achieve energy densities comparable to nuclear weapons, but sustained over volumes millions of times larger and for durations thousands of times longer. The physics of concentrating such enormous energies in such small spaces pushes into regimes where quantum mechanics, general relativity, and plasma physics all interact in ways that are poorly understood, even by leading theorists. The leading explanation involves magnetars, neutron stars with magnetic fields roughly 100 million times stronger than the most powerful magnets humans have ever created. These cosmic magnets represent some of the most extreme objects known to exist, where magnetic field energy alone can exceed the binding energy holding the neutron star together. When such objects undergo catastrophic magnetic reconfiguration events, they can theoretically release energies on the scale observed in fast radio bursts. But even magnetar models face serious challenges when confronted with the most energetic fast radio bursts. The magnetic field energy available in a typical magnetar is sufficient to explain modest fast radio bursts, but the most powerful events require energies that would essentially destroy the magnetar entirely. This has led theorists to consider exotic scenarios involving supermagnetars with magnetic fields approaching theoretical limits, or complex multi-object systems where multiple compact objects interact catastrophically. Recent theoretical work by Dr. Yuanpei Yang and colleagues has explored whether neutron star mergers could produce fast radio burst-like signals during their final moments before collision. These merger precursor models suggest that the extreme tidal forces operating during the last milliseconds before neutron stars touch could trigger magnetic field instabilities powerful enough to generate brief, intense radio bursts. Alternative theories venture into even more exotic territory. Some models propose that fast radio bursts could result from the collapse of exotic matter states that exist only under the most extreme conditions. Strange quark matter, a theoretical phase where individual quarks exist freely rather than being confined within protons and neutrons, could potentially undergo phase transitions that release enormous energies very rapidly. Even more speculative ideas involve primordial black holes, hypothetical microscopic black holes left over from the early universe that could evaporate through Hawking radiation on timescales matching fast radio burst durations. While such objects remain purely theoretical, they represent the kind of exotic physics that might be required to explain the most extreme fast radio burst energetics. The energy mystery deepens when astronomers consider the coherence properties of fast radio burst radiation. Unlike thermal radiation from hot objects, which emerges as random, incoherent photons, fast radio bursts produce highly organized, coherent radio waves that suggest some form of cosmic laser mechanism. Maintaining coherence across the enormous volumes and energies involved in fast radio burst production requires physical processes that operate with extraordinary precision. Dr. Maxim Ludikov of Purdue University has developed models based on relativistic plasma physics that attempt to explain how coherent radio emission can be generated in magnetar environments. These models invoke complex interactions between charged particles accelerated to nearly the speed of light and the intense magnetic field surrounding neutron stars, creating conditions where coherent radio waves can be amplified through processes similar to those operating in human-made masers and lasers. The coherent nature of fast radio burst emission creates additional constraints that theoretical models must satisfy. The radiation must remain organized over distances much larger than the source object itself, requiring some form of collimation or focusing mechanism that can maintain beam coherence across interstellar scales. This focusing requirement adds another layer of complexity to an already challenging theoretical puzzle. Recent observations have revealed that some fast radio bursts exhibit multiple emission components occurring on microsecond timescales. Variations in intensity that happen faster than light can cross the diameter of most neutron stars. This subburst structure suggests that fast radio burst emission mechanisms operate with temporal precision that approaches fundamental physical limits. The energy mystery extends beyond just the radio emission to encompass the total energy budget of fast radio burst events. Multi-wavelength observations have revealed that some bursts are accompanied by X-ray and gamma-ray emission, suggesting that radio represents only a fraction of the total energy released. If fast radio bursts are part of broader electromagnetic outbursts, the total energies involved could be even more extreme than radio observations alone suggest. Dr. Christopher Bokanek and colleagues recently detected simultaneous X-ray and radio emission from the galactic magnetar SGR 1935 plus 2154, providing the first direct evidence for multi-wavelength fast radio burst emission. The energy released in X-rays during this event was roughly 1,000 times greater than the radio emission, implying that typical fast radio bursts might represent only the tip of an energy iceberg. This multi-wavelength perspective raises profound questions about the fundamental nature of fast radio burst emission. If these events involve total energies far exceeding what radio observations suggest, then the theoretical challenges become even more severe. The physics must not only explain how such enormous energies can be generated and released rapidly, but also how they can be partitioned across different electromagnetic wavelengths through mechanisms that remain completely mysterious. The energy mystery also encompasses temporal aspects that challenge our understanding of causality in extreme environments. Some fast radio bursts show evidence of internal structure that varies on timescales much shorter than the light-crossing time of their presumed source regions. This apparent violation of causality constraints suggests either that fast radio burst sources are much smaller than expected, or that the emission mechanisms involve relativistic effects that can compress apparent timescales. One promising approach to resolving the energy mystery involves studying the environments surrounding fast radio burst sources. If these events require specific environmental conditions, dense stellar winds, strong ambient magnetic fields, or particular plasma densities, then understanding these environmental requirements could provide crucial clues about the emission mechanisms themselves. Recent observations of repeating fast radio burst sources have revealed systematic changes in burst properties over time, suggesting that the source environments evolve on observable timescales. These evolutionary studies provide unique opportunities to probe the physics of extreme magnetic field environments and their role in fast radio burst production. The energy mystery ultimately forces us to confront the possibility that fast radio bursts represent entirely new physical phenomena that operate beyond the boundaries of conventional astrophysics. They might be our first observational evidence for exotic states of matter, extreme magnetic field effects, or relativistic plasma processes that push into previously unexplored regimes of physics. Understanding the energy mystery requires not just theoretical advances, but also observational breakthroughs that can provide more detailed information about fast radio burst emission mechanisms. Future observations with more sensitive telescopes and broader frequency coverage will be essential for distinguishing between competing theoretical models and advancing our understanding of these extraordinary cosmic phenomena. The energy mystery of fast radio bursts continues to challenge our most fundamental assumptions about how matter and energy behave under extreme conditions, pushing theoretical physics into uncharted territory where new discoveries about the nature of reality itself might emerge. Chapter 7: Galactic Outburst: The discovery that fast radio bursts could originate from within our own galaxy transform these mysterious events from distant cosmic curiosities into immediate, observable phenomena that threaten our understanding of stellar evolution and galactic dynamics. When SGR 1935, 2154, a known magnetar located just 30,000 light-years from Earth, produced a fast radio burst on April 28, 2020. It provided astronomers with their first opportunity to study one of these cosmic explosions in unprecedented detail. The galactic fast radio burst was detected simultaneously by multiple space-based X-ray telescopes and radio observatories around the world, creating the most comprehensive multi-wavelength observation of a fast radio burst event ever achieved. Unlike the distant extragalactic bursts that arrive as faint radio whispers after billions of years of travel, this galactic event was close enough to reveal internal structure, environmental conditions, and associated emission that had remained hidden in previous observations. Dr. Christopher Bokanek of Caltech led the analysis of radio observations from the STAR-E2 telescope network, revealing that the galactic burst lasted approximately 1.6 milliseconds and released roughly 1.6 times 1028 ergs of energy in radio waves alone. While this energy is modest by fast radio burst standards, about 1,000,000 times weaker than typical extragalactic events, it still represents more energy than the Sun produces in radio waves over several months, all concentrated into less than 2 milliseconds. The simultaneous X-ray observations told an even more dramatic story. The Fermi Gamma Ray Space Telescope, the Neil Gehrels Swift Observatory, and other space-based instruments detected intense X-ray and soft gamma ray emission that began roughly simultaneously with the radio burst and continued for several minutes afterward. The total energy released in high-energy photons exceeded the radio energy by factors of thousands, suggesting that fast radio bursts might represent only a small fraction of the total electromagnetic energy released during these cosmic catastrophes. This energy discrepancy provided crucial insights into fast radio burst physics. The fact that such enormous energies could be channeled into radio emission suggested highly efficient conversion mechanisms operating under extreme conditions. The physics must somehow take the thermal and magnetic energy available in magnetar environments and convert it to coherent radio waves with efficiencies far exceeding anything achieved in human technology. The galactic fast radio burst also revealed unprecedented details about the emission environment. Unlike distant bursts, which appear as point sources even in our most powerful telescopes, the galactic event was close enough to study the surrounding stellar region directly. The burst originated from a known magnetar that had been monitored by X-ray telescopes for years, providing detailed information about the source object's magnetic field strength, rotation rate, and emission history. SGR 1935 plus 2154 represents an extreme example even among magnetars. Its magnetic field strength approaches YP Gauss, roughly 1 trillion times stronger than Earth's magnetic field, and powerful enough to distort the quantum vacuum of space itself. The neutron star rotates once every 3.24 seconds, which is relatively slow for a pulsar, but creates enormous rotational energies due to the star's extreme density. The timing of the galactic fast radio burst provided crucial evidence linking these events to magnetar activity. The radio burst occurred during a period of enhanced X-ray activity from SGR 1935 plus 2154, suggesting a direct connection between magnetic field reconfiguration and radio emission. This correlation finally provided the smoking gun, evidence that astronomers had been seeking to connect fast radio bursts with specific astrophysical objects and processes. But the galactic burst also revealed puzzling differences from extragalactic fast radio bursts that complicate simple extrapolation between local and distant events. The galactic burst showed different spectral characteristics, polarization properties, and duration compared to typical extragalactic bursts, raising questions about whether all fast radio bursts share common emission mechanisms or whether multiple distinct physical processes might produce similar observational signatures. The environmental studies of SGR 1935 plus 2154 have revealed that magnetars can influence their surroundings across scales far larger than the neutron stars themselves. The intense magnetic fields extend into the surrounding interstellar medium, creating complex plasma environments where charged particles can be accelerated to relativistic speeds and magnetic field lines can undergo catastrophic reconfiguration events. Dr. Kenzie, Nimmo and colleagues use very long baseline interferometry to study the precise location of fast radio burst emission within the SGR 1935 plus 2154 system, revealing that the radio waves originated from regions several thousand kilometers from the neutron star surface. This observation suggests that fast radio burst emission involves extended magnetospheric processes rather than surface phenomena, adding complexity to theoretical models of burst production. The galactic fast radio burst has also provided insights into how these events might affect planetary environments. At a distance of 30,000 light-years, the radio burst arrived at Earth with an intensity roughly 1 billion times weaker than a cell phone signal. However, calculations suggest that planets located within a few hundred light-years of the source would have experienced radio intensities comparable to powerful radar systems, potentially affecting planetary atmospheres and magnetic fields. This proximity effect raises intriguing questions about the potential impact of fast radio bursts on planetary habitability. If these events are as common as modern surveys suggest, then most planetary systems will occasionally experience intense radio bombardment from galactic fast radio burst sources. While the biological effects of such exposure remain unknown, the possibility that fast radio bursts could influence planetary evolution on galactic scales represents an entirely new consideration for astrobiology. The study of SGR 193-52154 has also revealed that magnetar activity can vary dramatically over timescales ranging from milliseconds to years. The source has produced multiple smaller radio bursts since the initial major event, each providing additional information about the physics operating in extreme magnetic field environments. These follow-up observations suggest that magnetar radio emission might be more common than previously suspected, with most events falling below detection thresholds of current telescopes. Recent observations have detected periodic variations in radio emission from SGR 1935 plus 2154 that correlate with the neutron star's rotation period, suggesting that magnetar radio emission might involve geometric effects similar to those operating in conventional pulsars. However, the enormous energies involved in fast radio burst production require additional physics beyond simple rotational modulation. The galactic fast radio burst has provided the first opportunity to study how these events propagate through known interstellar environments. The radio waves from SGR 193-52154 traveled through regions of the Milky Way that have been mapped by other astronomical surveys, allowing astronomers to study how fast radio burst signals are modified by interstellar plasma and magnetic fields. These propagation studies have revealed that even within our own galaxy, radio signals can be significantly modified during their journey from source to Earth. The galactic fast radio burst showed evidence of scattering by interstellar plasma clouds, frequency-dependent delays from dispersion, and polarization rotation from magnetic fields, all effects that must be carefully accounted for when studying more distant fast radio bursts. The environmental context of SGR 193-52154 has also provided insights into magnetar formation and evolution. The source appears to be located in a region of the galaxy with relatively low stellar density and little recent star formation activity, suggesting that magnetars can survive and remain active for much longer periods than initially expected. This longevity has important implications for fast radio burst rates and the cosmic evolution of these phenomena. Perhaps most significantly, the galactic fast radio burst demonstrated that these cosmic explosions can occur essentially anywhere within our galaxy, including regions relatively close to Earth. This proximity means that future galactic fast radio bursts might be detectable with much simpler instruments, potentially enabling amateur astronomers and citizen scientists to participate in fast radio burst research. The success of multi-wavelength observations of SGR 1935 plus 2154 has inspired new observation strategies for studying fast radio bursts across the electromagnetic spectrum. Future surveys will combine radio telescopes with X-ray and gamma-ray detectors to search for correlated emission from distant fast radio burst sources, potentially revealing whether multi-wavelength emission is a universal property of these events. The galactic outburst has fundamentally changed our understanding of fast radio bursts, from mysterious distant phenomena to observable local events that we can study in extraordinary detail, providing a crucial bridge between theory and observation that continues to drive new discoveries about the most extreme magnetic environments in the universe. Chapter 8. Time Prison. The temporal nature of fast radio bursts represents perhaps their most profound challenge to human intuition and scientific understanding. These cosmic events unfold on timescales so brief that conventional concepts of causality, information transfer, and physical process development begin to break down. To truly comprehend fast radio bursts, we must venture into a realm where time itself becomes a constraining prison that limits what physics can accomplish. Consider the fundamental temporal constraint governing fast radio burst emission. Everything that happens during these events must occur within a window typically lasting less than 5 milliseconds. This means that from the initial trigger through energy accumulation, particle acceleration, radiation generation, and signal escape, the entire cosmic catastrophe must unfold faster than a human heartbeat. No other astronomical phenomenon operates under such extreme temporal pressure. Dr. Maxim Lyudakov of Purdue University has calculated that this temporal compression creates what he terms causality horizons, fundamental limits on how large fast radio burst emission regions can be based purely on the speed of light. Since information cannot travel faster than light, different parts of a fast radio burst source region, separated by more than about 1,500 kilometers, cannot coordinate their activity during a typical burst duration. This causality constraint forces fast radio burst sources to be remarkably compact. While neutron stars themselves are only about 20 kilometers in diameter, their magnetospheres, the regions where magnetic field effects dominate, can extend for thousands of kilometers. The temporal prison of fast radio burst emission means that only small portions of these extended magnetospheres can participate coherently in any individual burst. The time prison becomes even more constraining when we consider the internal structure observed in many fast radio bursts. High-resolution observations reveal that some bursts contain multiple subpulses separated by microseconds, temporal variations that occur on timescales much shorter than the overall burst duration. These substructures suggest that whatever mechanism produces fast radio bursts operates with temporal precision approaching fundamental physical limits. Dr. Ziggy Plunis and colleagues have analyzed the microsecond scale structure of fast radio bursts detected by the CHIME telescope, revealing patterns that suggest highly organized emission processes. Some bursts show regular spacing between subpulses, as if the emission mechanism were operating like a cosmic clock with microsecond precision. Others display more chaotic internal structure, possibly reflecting turbulent processes in the emission environment. The temporal precision required for such organized emission challenges our understanding of how physical processes can maintain coherence under extreme conditions. In terrestrial physics, achieving microsecond timing precision requires sophisticated control systems and carefully isolated environments. For astronomical objects to achieve similar precision while generating galactic-scale energies suggests physical mechanisms operating at the intersection of classical and quantum regimes. One of the most puzzling aspects of the time prison involves what astronomers call the bandwidth-duration relationship, the observation that shorter bursts tend to cover broader frequency ranges while longer bursts are more narrowband. This relationship suggests that the temporal compression of fast radio burst emission is fundamentally linked to the physics of how radio waves are generated and organized. The relationship between time and frequency in fast radio burst emission might reflect quantum mechanical constraints on how electromagnetic energy can be packaged and released. Quantum mechanics imposes fundamental limits on the simultaneous precision of time and frequency measurements, a principle known as the time-frequency uncertainty relation. Fast radio bursts might be pushing against these quantum limits, representing astronomical phenomena where quantum mechanical effects become important on cosmic scales. Recent theoretical work by Dr. Ben Margalit and colleagues suggests that the time prison of fast radio burst emission might be imposed by the finite light-crossing time of neutron star magnetospheres. As magnetic field lines reconfigure during a magnetar starquake, information about the reconfiguration can only propagate at the speed of light. This creates natural timescales for magnetospheric activity that match observed fast radio burst durations. However, the time prison extends beyond simple light-crossing times to encompass more fundamental questions about energy storage and release in extreme magnetic environments. The magnetic field energy available in magnetar environments must be accumulated over much longer timescales than fast radio burst durations, possibly years or decades of gradual magnetic stress buildup before catastrophic release in milliseconds. This energy storage timescale mismatch creates what theorists call the energy reservoir problem, explaining how enormous energies accumulated slowly can be released coherently and rapidly. The solution likely involves some form of magnetic instability that can trigger avalanche-like energy release, converting stored magnetic energy to electromagnetic radiation with extraordinary efficiency. Dr. Andrei Bolobarov of Columbia University has developed models where magnetic field instabilities in neutron star crusts can trigger cascading processes that release energy much faster than it was originally stored. These magnetic avalanche models suggest that fast radio bursts might represent the electromagnetic signatures of catastrophic magnetic reconfiguration events that reorganize entire neutron star magnetospheres in milliseconds. The time prison also creates unique observational challenges for studying fast radio burst physics. Traditional astronomical techniques rely on observing objects over extended periods to understand their behavior and properties. Fast radio bursts essentially compress all their observable activity into timescales too brief for conventional analysis techniques. This temporal compression has driven the development of new observational approaches specifically designed for millisecond phenomena. Modern fast radio burst detection systems can capture and analyze radio signals with temporal resolution measured in microseconds, revealing structural details that would be impossible to detect with traditional astronomical instruments. The study of fast radio burst timing has also revealed connections to fundamental physics that extend beyond astrophysics into tests of relativity and quantum mechanics. The precise timing of radio wave arrival across different frequencies can be used to test whether the speed of light is truly constant for all photon energies, providing some of the most sensitive tests ever achieved for potential violations of Einstein's special relativity. Some theoretical models suggest that fast radio bursts might probe physics at the interface between quantum mechanics and general relativity, where spacetime itself might exhibit quantum properties. The extreme energies and brief timescales involved in these events could potentially reveal signatures of quantum gravity effects that are completely undetectable in less extreme environments. The time prison of fast radio burst emission has also inspired new theoretical frameworks for understanding how information and energy can be organized in extreme astrophysical environments. These events suggest that nature has mechanisms for achieving temporal precision and energy concentration that far exceed anything possible with human technology. Recent studies of fast radio burst polarization have revealed that the emission maintains organized electromagnetic field orientations across the entire duration of individual bursts. This polarization coherence suggests that the underlying emission mechanism can maintain quantum mechanical organization over timescales and energy scales that challenge conventional understanding of decoherence processes in chaotic astrophysical environments. The implications of the time prison extend beyond astrophysics to fundamental questions about the nature of time itself in extreme gravitational and electromagnetic environments. Fast radio bursts occur in spacetime regions where gravitational time dilation, electromagnetic field effects, and relativistic particle motion all interact in ways that are poorly understood theoretically. Understanding how time operates during fast radio burst emission might require new theoretical frameworks that combine general relativity, quantum field theory, and plasma physics in ways that have never been attempted. These events represent natural laboratories for studying Physics under conditions that cannot be replicated in any terrestrial experiment. The temporal prison of fast radio bursts ultimately forces us to confront the fundamental limits of what can happen when time becomes the most constraining factor in cosmic phenomena, revealing aspects of physics that operate at the intersection of space, time, energy, and information in ways we are only beginning to understand.